Okay, hello everyone. I think we have studied the chapter 14 until the directional derivative. How to maximize the directional derivative, uh, which is we can see how to maximize, and basically you need to take the magnitude value of the vectors, of the gradient vectors, and then in conclusions the minimum will be the negative of the value. Okay, that is, and this is some example here, with a function of temperature in space, and then the question is asking in which directions does the temperature increase fastest, which means we need to find the gradient factors in 1, 1, -2 coordinates. And then when is the max rate of increase? Max rate of increase, we need to calculate the first the gradient factor and then find the value. And within that value, that will be the maximum rate of increase. Okay. Now, if we move on, we're still in the chapter 14.6, but we will have another sections about the tangent plane. Okay, so it is called the tangent plane. To level surface. So let me put the picture first. Okay. So from what we have discussed before, we know that if this blue one, the S1 is our surface, and at some point P, we can make out our plane, our tangent plane. Okay. And there is a curve C on the surface S, which has the factor R, and the factor R will have at point P will have the R prime T0 with a parametric T. Okay. Let me write some notes here. So let the S be a surface, okay, with the equations and equal a constant. So this means, okay, this is a level surface of function of 3 variables. All 3 variables functions is the same. So K is usually it's a constant that represent the surface level. Okay, but we will talk about that maybe later. Usually we are using this kind of functions to visualize a contour, like you have in your map, right? You have a map of a mountain, and you will see there will be a different color, like maybe this part is more light, and the more it goes white, it's more dark. The dark color means it's much more lower in the height, right? And we can take the differences between each of these 3 area with some constant K, and the constant K will be different, and it will show the level of the surface. Okay, but we will talk about that later. Okay, back to this picture. So let the point P is on this coordinate, okay, and the point P is on the surface, and then we have also C there. It's curve also on the surface S, okay, that pass through, and our C is having a parametric equations, a factor functions. Okay, and then let P also correspond to T0. So x0, y0, and z0, this is correspond to the T0. So when T is equal T0, uh, the coordinate is x0, y0, and z0. And then we can write, because C is also on the surface, we can write the function and then we differentiate with respect to T, or let me take this is partial differentiation with respect to T, like that. Then we will get, this will be dou f dou x, and then the x dt, okay, and then plus and then plus is equal 0. Let me make it a little bit closer. Okay. Okay, now we have this expressions in which we can also look this expression as, look at this partial here, all this partial, okay, partial x, y, and z. All those partial is actually our gradient factor, right? Okay. And this part here is dx over dt, dy dt, and dz over dt is our r prime. So this is actually a dot product of our gradient factor and our r prime, our tangent, right? And it is equal 0, which means from this expression we know that this will be orthogonal. Or we can say that the gradient factor is orthogonal to the r prime. This is gradient factor, and this is the, we can write this as a tangent factor if you remember the big T, okay, because it has the same direction as the r prime, right? So when we look at the actual picture, we can see that this is true, that it is orthogonal, right? This is the gradient factor. This is the r prime, or we can just say that that's the tangent factor, right? So we can simply write, okay, maybe right here, or let me write here. So that's the conclusions. When, let's say, t is equal to 0, the corresponding time, we have the r will be x0, y0, and z0. Okay. And then let me maybe a little bit lower. And let me write this in this one more time. This. Okay, and then we can also write on this point. It's also 0. Okay. And then we can thus we can find the equation of tangent plane. So we can define tangent plane to the level surface. This level surface of xyz equal k at x0 z0, right? And then the normal vector, if we look at the normal vector, is the gradient vector, right? So remember that if you have the normal vector, let's say the n, you have a, b, c, or c, d, right? And this is we called also direction number, right? And this will recreate the plane that we are going to write, right? So we can have that like that. Okay, this is just a notes. So we can write the equation. Equation will be partial x from the big F at just maybe just directly the formula. Of course, you get it that this partial x is, of course, at this point. Okay, we already defined that. So x minus x0 plus partial y minus y0 plus partial z minus c0. And this is equal 0. Okay. Or we can write this in terms of gradient vector at point P dot the r minus r0. We can set up a dot product. So this is the general equation. Or maybe you want to make a symmetric form. This is also, we can write that. Usually we write this to define or to show the, or maybe just write this is the normal line, right? Or we can write this is actually our symmetric form or symmetric equations, in which this is the direction number, right? Okay. Okay. Maybe one example, and then can move to another section. Okay, maybe write example here. Example. So find equations of tangent plane and normal line. It's similar to, I think, your last quiz. But now we are using the tangent plane on the level surface at -2, 1, -3 to the equation x squared 4 y squared. Okay. And what is this structure? This is, if you remember, you have all positive and all having squared, x squared, y squared, z squared. This is the ellipsoid, right? Now first, because this example didn't mention specific with the functions, right? So we need to define the function by ourselves. So let's define the functions by f. Okay. And let's just write x squared you can write just like this. No need to include this 3 because we don't really need 3, right? Because we differentiate and of course constant will be 0. So we don't really need to write that. So just write this function and then we can write the gradient factor. Okay. So it is this is partial x, partial y, partial z, right? And we can write each one is become x over 2, 2y, and then 2z over 9, right? And then we can write the gradient factor at the specific point that we want to observe. And this is -1, 2, and -2 over 3. Okay. You can use the dot product, or simply you can write the general equation. But let me just write this so that you can have idea. So the gradient factor will be 1, 2. This should be equal 0. 2 and -2 over 3 dot the I think this should be factor. Sorry. All right, I think that's I think same thing when you minus this and you want to make it into 3 axis. It's the same. So x plus 2, y minus 1, and then z plus 3. Then we can simplify. Sorry, this minus, and then minus x plus 2 plus 2, y minus 1, 2 over 3, z plus 3 equals 0. And you can solve this and find the equation of tangent plane. This is the equation of tangent plane. But please, every time you see the tangent plane equation, make sure you solve until the simplest form. Okay, until the simplest form. And the normal line will be x plus 2 -1 equal. Let me just write -2 over 3 like that. Okay, you can write it like this for the normal line. Okay. Okay, that's it. The tangent planes to level surface. Okay, before we continue, is there any questions? You can type the question if you want in the chat box. I will look later. Okay, maybe I'm adding some notes. Okay, so what will happen? Okay, if the surface in the form of z equal just two variables. Okay? Before we have here, we did all the things with the three variables, right? Oh, sorry. Okay. So how we are supposed to write? Okay. So we need to define the these three variables again. So we need to convert this two variables into the three variables. So we can write, okay, we can write move z here, so it's become negative c, and that is our functions. Okay, so we can use this in our calculation. So the gradient vector will be, this is partial x, partial y, and then this is just negative 1. And what happened with the tangent plane? So what's the conclusion from all of this, the tangent plane to the level surface? So you can basically do everything, not necessarily need to be three variables, but you can also use it for two variables. Okay. The key is to make out these functions. Okay. So you need to make this big F function to define your case or your problem. Okay. So you can use it in every most of the cases. Okay. I think there are some notes at the last section on 14.6, but I think that is pretty similar or on what we have learned before. So I will skip that. And I will focus now on 14.7, which is the max and min values. It's pretty much same as your calculus 1, what we need to find, right? So in calculus 1, max or min, how to find, right? Or how to find the local or absolute, right? The first thing we have learned in calculus 1 is about the critical point. So if you remember critical point, okay, you can also take a review a little bit if you want. What is the critical point means? The critical point is at every point that when you derive the functions, it should be 0. So it could be a minimum, it could be a maximum, it could be just a critical point without maximum or minimum. It doesn't matter. But every maximum and minimum, it should have this f prime equals 0. And you can also look at the second derivative, right? To look at the concavity, right? When will be concavity up, down, etc. And now in calculus 2, because at least we need to have two variables in our observations, then or maybe I will just put in the picture. Okay, this is pretty much example or how we are going to show the maximum and minimum. from the graph. Okay. So of course, the picture you see here, let's say we are limiting our restrictions to only on this picture. So every time you see the lowest one, that should be the absolute minimum. The highest one should be the absolute maximum. And if you have in between, it will be the local. It can be local minimum or local maximum. Okay. Okay, let's take some definition here. General definition. Function f has a local max at, let's say, this point, x0, 0, if x is a disk center at x0, y0, such that f is greater than for all point in x, y in the disk. So the disk is kind of like the restriction area that we want to observe. Okay. And f has a local mean at x0, y0. Same, and then you write such that this is less equal. Okay. And then the absolute max will be defined as for all points in domain, and absolute mean for all points in domain. Okay, same. So if we look here, let's say this local maximum here, maybe it's about here. And if we look at the point here, let's say this is the disk. Okay. Or maybe let give more. So when we look at this disk, the right one here, that is our restrictions to look at the x0, y0. Okay. I think if you just look at the picture, you know how to describe these words. Okay? This is just to describe all the phenomenon in more rigorous or in more exact numbers in math. Okay. Okay. From here, actually, we also can rewrite the theorem. We can write the theorem based on calculus 1, the Fermat, if you remember. So if f has local max or minimum at, let's say, point A, B, or maybe let's just use the same x0, y0. And the first order partial derivatives of the function f also exists here, then we have this it's actually the same thing as a critical point. Okay, let's just say that that's the similarity with it with calculus 1. But to make it more clear, what's the difference between the how we are observing the 2-dimension and 3-dimension? We can have the, it's called the bounded sets. If you have area like that in a 2-dimension, or maybe any function that you want to observe the minimum or maximum, you can take some box like this and make a bounded sets. Okay? In 3-dimension, let's make more clear. Okay. In 3-dimension, you have maybe like that, maybe more curvy. So we take the box in 3 dimensions. And also, this is another theorem that's showing how we can define the extreme value or the maximum value. So if our function of 2 variables x, y is continuous on a closed and bounded set of real number, then function has both absolute max and absolute min. Okay. Okay. Another thing that is important in this maximum and minimum value. Okay. Let me make a new page, new section. Remember that we have this this surface. Okay. It's called the hyperbolic paraboloid. So if we look at the point in the middle here, I've said this before. If you want to look which one is max, which one is minimum, it's hard to say, right? But this is actually, if you look at the parabola that is making out that point, right? Or from here, you can also have parabola. It's actually one of the, we can say it's a critical point, right? But it's not max or minimum. It's called another terms. This is called the saddle point. But the definitions is precisely similar to what we are going through. The partial x is 0, the partial y is 0. But in saddle point, it is not max or min. Okay, That's the definition. So how do we know it is max or minimum? So whenever you find the partial x is 0, partial y is 0, you need to have another test to check whether it is really maximum, minimum, or it's just a saddle point. Then in calculus 2, that is the purpose or the goal of the second derivative test. Okay, let me write the definitions. So let the function be a function of two variables with continuous second order partials, which means you can derive and find the second order partials. Okay. In some disk centered around a critical point. Okay, critical point. Critical point is the point that makes the derivative is 0. Let's say the critical point x0, y0, and let we define d. Okay, this is the term. I think you can also say this is a determinant. So d is defined by the partial xx, partial yy minus the partial. Yeah, it's determinant. It's determinant. So it is AD minus BC, right? And the important thing here is from that t is if t is greater 0, we will have three conclusions from d. So if d is greater 0, I need to check the fxx should be greater, fxx is less. Now from here, this is local minimum, and this is local maximum. And if d is less than 0, then the point is a saddle point. And this, if equals 0, it's inconclusive. There is some how to prove this, but I think I will leave that maybe on the end of the chapter if we have time. So basically, you can obtain this this determinant and the proof from the directional derivative. But let's just continue first. Okay, maybe at the end of this section I will explain. Okay, any questions first? So at least now you can determine, which is the local max, local minimum, saddle point from the second derivative in partials. Okay, let's see if we have. Okay, maybe just examples for this case. Okay. Okay, let's start. First example. Let's say you have equation. The question is just find any local max, min, or saddle point. The first thing to do, just similar with the calculus one, find a critical point, right? So we need to find the partial x. And it should be equal 0. Okay, and then we find the partial y. It should be equal 0. And we need to solve this, okay, simultaneously. So this is x equal y. So we can also write these terms as this. And we can take out x. And we find the x is 0 and x is 4/3, right? Okay. So when x is 0, y is it's also 0, right? 0, 0, 0. Yeah. Oh yeah, because x is equal y, so you can just write it's the same, right? Okay. So critical point, and right here, critical point will be 0, 0, and 4/3, 4/3. Okay. But how do we know this is maximum minimum? We need to do the second derivative test. So second derivative test. Let me write the determinant. Okay. And now we can write the partial x. This will be -6x. Partial y. It will be -4. Okay. And then partial xy or partial yx, that will be the same, right? It will be 4. Okay, we have this. And we are using it for finding the determinant. So first is checking the first point, 0, 0. So D will be -6x. Okay, let me write this. And then Fy -4, -4 squared. Okay. And this will be 0. So it will be -16. So we know that this is less than 0, right? So we can conclude this is a saddle point. So 0, 0 is saddle point. Okay. 2. Checking forward 3 and forward 3. Because the calculations, mostly it's just having a constant. So I think it will be not too difficult, right? And plug in forward 3 here. It will be negative 24 over 3 is negative 8. So it will be 32 minus 16. So it's 16. So the D is greater 0. And we need to check the fxx. This is less 0, right? Because negative 6 is negative 8. It's less 0, right? So we can conclude from here that this is local max. And because there's only 2 points, then that is our conclusion from this example. Okay, any questions first? Maybe I will give you another example to make you more familiarized with the method. Okay, maybe another 2 example maybe. So another example, similar questions. So you have the function. Find extreme values. So if you have this kind of question, find extreme values, meaning it's finding the local max or minimum, or if they have saddle point, you need to mention the saddle point. Okay. Let me give you a couple minutes, maybe 2 or 3 minutes to try. And if you finish, you can mention which point that has a saddle point, if they have, which one is maximum, local max, local minimum. You have. Oh, let me give you just 3 minutes, 4 minutes to try. And please write your answer in the chat box. Okay. Anyone got the answer? Or maybe confused how to solve? uh, I think the point is good, but I think the yes, I think Shelly, you are correct. I think you, Rivaldo, you need to calculate. Uh, I think because the minus and positive, so you need to be careful. Okay, because if you think carefully, if you think that all those three is saddle point, it's kind of not making any sense, right? If you think that if there's three point and then all will be a saddle, it probably make non-logic in if you draw, if you have three saddle points, all three saddles. So at least there should be at least a difference. Okay. Okay. Let me go through here and look at the partial x. Okay. And partial y. And this should be 0. Should be 0. So we can substitute, right? So if you want to make maybe y is x cubed, and then going to put here. So for x minus 4, and then x cubed. So 4x minus 4x9. So please you get first is this x0, right? So x equals 0 from here. And you get 1 minus x to the power of 8, right? And this is maybe when you look at the equations, you look at this 8, right? It seems really maybe confuse you how to solve, but it's actually, if you think that the x with the power of 8 is from the x with the power of 4, you can this into this form, right? And you can take this in more and leave the 1 plus x with the power of 4, and it's equal 0. So you have s equals 0, s equal plus minus 1, right? This will be not conclusive, and this also not conclusive. So this is just our point that we can obtain the real numbers that we can obtain. Okay, the other is maybe imaginary, so we don't really need to pay attention to the imaginary number. Okay, the next one is we take the second derivative. So this is critical point. If you want to write clearly, this is critical point, right? The partial xx is negative 12x squared. Partial yy is negative 12y squared, and then partial xy is 4. Okay, so we have this, and we have the point. What you can do is you can also write the table to make it more clear. So this is the critical point. Critical point. This is D. This is the partial XX. This is the conclusions. The critical point 0, 0, right? And the other one is 1, 1, and then negative 1, negative 1. Okay. The D, let me write here, D is fyy minus fxy and then squared. So for 0, 0, if you look at the partial xx, this should be 0 minus 4 squared. So it's less 0, right? So it's, or we can just write this is become negative, or D is less 0. So we can conclude this is saddle point. And 1, 1 is negative 12, negative 12. So it's already positive, minus 16. So it should be positive, right? 144 should be positive. And then another case is negative 1 squared. It's another positive. So it's the same. So it's the same number, right? The partial xx, if you take the number, it will be negative, right? It will be less than 0. This is also less than 0. So this is local max. This is also local max. Okay, another example that you can also observe, but I think I won't give to you in detail, but just let me show you. Remember in calculus 1, you have the like a story to make a possible maximum value or minimum value. Like for example, find the shortest distance, right? Find the maximum value. The idea is still the same. Basically, we need to find the critical point. But first, we need to find the formula that can relate with the problem, and then we need to maximize or minimize the problem, the formula, and find the critical point, which gives the either the minimum or the maximum. Okay. So you need to check this out. Maybe this weekend, maybe I'm giving you maybe small exercise, just exercise to help you to get familiarized with the problem in chapter 14. Okay. Let me continue to give you some sets of another notes about the absolute maximum and minimum. But this is actually all the things in absolute maximum and minimum is basically the same thing as in local max and minimum. The difference is just how we are going to observe the value. Okay, so let me write some words here. So if f continues on closed and bounded sets, okay, in domain in real number, f will attain maximum value and it should be absolute maximum value and absolute minimum value. Let me make the difference. Okay, let me make difference. So maybe this is 1 and then this is 2. at some point. First, we really make the point x1, 1, and x2, y2. Also in the domain. And to find the absolute maximum value and minimum value, what you need to do to find absolute max or min, what we need to find is find critical point in the domain, and then find the extreme value. Extreme values means you need to use the second derivative. And then check the point, and the largest value will be the absolute max. Okay. And the smallest value will be the absolute minimum. And then evaluate the boundary. It's not really that important, but I think this tree itself is already enough to determine the absolute maximum and absolute minimum. Okay. Okay. Basically, it's the same thing in the local max and local min. The difference is you need just to measure the absolute in domain. Okay. While the local, you can maybe having a interval in some set of interval of x and y. That's also possible. Okay, next thing. Before we go into it's so we already finished 14.7 actually. So before we going to move on and going to the last section 14.8, I think we still have time to give you the proof why we need to use the second partial. So if you remember, let's take this as our directional derivative of f in direction. Let's say the factor is h and k in x-axis and y-axis. So we get these terms, okay? And then if we apply the directional derivative twice, okay, which means you need to take second derivative, or let me just write, so directional derivative and then directional derivative. So we derive twice with directional derivative, which means we need to take the derivative from this partial x partial y, right? Then let me write, this is the partial x. Let me just write this directional derivative and then h, and then plus the partial y, and then k. If you look at here, f a partial x and partial y, when we take partial with x, we will have partial x and partial y x, right? Okay. So we will get partial x and h, and plus partial y x and h. sorry, k, and then h. And then plus, we take partial y with, so partial x, y, right? Partial x, y, h, plus partial y, y, k, and it's k. Okay. And we have now partial x, x, and h squared, partial y, x, k, h, or hk is same, uh, plus, because this yx and xy is the same, we can plus this 2, and let's say this become xy. This is hk plus f k squared. Okay, now imagine this is a constant. This is a variables. So actually, you can see that this is, you can make it in some quadratic formula, right? And because it's quadratic, let's take complete square. Okay, so complete square. So these expressions will be, this will be h plus okay. And we are given that the partial x at some point, this should be greater 0, and d should be greater 0. Okay, and but partial x and d equal x y y. Let me write the formula. This is, they are continuous function. So there is some b. Let's say this is this with center of x0, y0, and radius. Let's say the radius is just a delta that is positive, such that this should be greater 0, or it's in all xy. Should be greater 0, and d should be greater 0. So this is true for every, no, only in direction. It's true in direction of vector u. Okay, yeah, more or less, but I think this is just to show how to find the formula. Okay, so basically you are taking directional derivative twice, and you get these notions. And this is just to prove that if you get this, then this is will be the local max, because it will be going above the other points. Okay, I think I will move to the next sections to give you another point of view on 14.8. Okay. This is actually similar to uh, finding the extreme value, but with another method. Okay. So it's called the Lagrange multipliers. I'm not sure whether you have heard before Lagrange. Um, I think you will be also familiar in the future, because I think you will be using the same method in other course. Okay, okay. Imagine you have let's say a map, okay, a counter map, like for example this. Okay, it's a counter map. Okay, let's make more sufficient. Okay, and then let's take some notes. So let's say this is a level surface. So level surface, maybe this is 10. This level surface is maybe 9. This level surface is probably 8. And this level surface is maybe 7. So each will have a different height, a different height. And let's say we have another functions, okay, that is, maybe we name it as g, function g, and it's another uh, level surface. Okay, what's the point of all this? Okay, so this, the red color is the known value, right? The known value. So we know this level surface, the constant. We know the constant. But this is the unknown value, right? The Lagrange method, basically, we are going to approach this unknown value with some known value. Okay. So let me write here. So we seek, or we need to find the extreme value of the functions of xy when the point is restricted to lie on the level curve. Oh, sorry. I think this should be known value. Sorry. This is known function. This is unknown max or min. Okay, sorry, that's how it. And then to maximize the function f, subject to function g, so this means we need to finding largest value of c of such that the level curve of f is equal c. Intersect, this will intersect g. Okay. So what does it mean? We need to find and try maybe different color. So we need to check whether 1, 2, 3, 4, this all this line. We need to find and check, and which one is intersect at this g for this f. Okay. So when we find the intersections, intersect means touching each other, right? So meaning the normal line at the same point here will be identical. And as a consequence of this normal line being identical, the gradient factor for both f and g will be parallel, right? Do you get it, what I mean? So here, if you have this, at this point here, if that is the intersection, when you have the gradient factor in this point, both gradient factor of the f and g, they both will be parallel. They have the same directions, right? So we can have, okay, gradient factor of f at this point is equal and what we need to find is actually we need to find this scalar that is multiplied the other gradient factor. And this is, we call the Lagrange. Okay, it seems a little bit complicated, but actually in the practical parts, it's not too difficult. Okay, so Lagrange multiplier uh, is a one method to find maximum minimum value if you have a functions that you want to approach and you have a constraint. Okay, you have a constraint. This will be the constraint. This function of g will be the constraint. This f, you need to find max or min value. Okay, maybe let me give you example. Maybe it's easier from example. So you have functions of f. And you have also g. Or maybe just make equations. And 3x plus 2y negative 8z is negative 50. Use Lagrange multiplier to find max or minimum value. Okay, if you look at this, of course, this is the one that we want to look for, the f, right? To find the maximum and minimum value of the functions. And the second equation here, this will be our constraint. Okay. Okay. Now, the constraint, let's say g, we can take g as 3x plus 2y negative 8z, just that. Because we only need the variables. Because when we differentiate, the constant will be 0, right? So what we need to do, we take the gradient factor equaling the Lagrange of the gradient g. So what does it mean? We take each axis. So this will be Lagrange. And partial y, this also will be Lagrange, and partial z, also Lagrange, and z. So each will be calculated. So partial x of f should be 6x, right? And this is Lagrange, and then the partial g will be 3. Okay. And we can solve for x is or you can say the symbols is lambda actually. And partial y is 2y, and lambda is 2. So y is lambda. And this for z and negative 8 lambda. Right? And z will be 2 lambda. So we have x, y, and z. And there are several methods to solve. Okay, but basically what you need to do is you need to find the relations between the x, y, z with lambda. And either way, you can take it to the constraint for all the lambda and take back to the original constraint. This is negative 50. And compute this, and we get this is negative 25 lambda. Okay. And lambda will be 4. Then we get x is 2, y is 4, and z is 8. And check the point. So at f 2, 4, 8, if you check, it will be, if you plug into the functions, so 3, this will resulting negative 100, right? And from here, we can actually say that this is the minimum value that we get. You can check maybe to check whether all the other values are, maybe checking 0, 0, 0, it's 0. Maybe checking the 1, 1, 1. This will be around 2. So it's above the negative 100. So 1 negative 100 is true that this is the minimum value. That's how we are using the Lagrange multipliers. And sometimes the Lagrange, when you solve through Lagrange, it's not always smooth as this. Sometimes you need to have several combinations of x, y, and z if it has more than one possibility. Okay, maybe I'm giving you another example, and then maybe not finishing the example. That's okay. You can try it at your home. So if this is the function, and this is the constraint, and use a Lagrange multiplier to find maximum or minimum value. Okay, let me just give you what we need to do. This is the Lagrange multiplier. First, we need to take that and take the, practically this is what we are going to do in all Lagrange method, the same method, but different solutions. Okay, how to solve it. So let's take the partial x will be yz equal lambda, and second one is 2x, just 2x. This is xz, and lambda 8y. This is xy, and 32z lambda. Okay, now we have lambda is yz by 2x, lambda is x by y. Okay, now we have all this solutions. So the idea of the Lagrange is we need just to solve and find x, y, and z. So previously you can find the lambda directly, right? And when you check to the constraint. So if you have this kind of equations, what can you do? If you check throughout the constraint here, so you need to take this squared and plus, plus, plus. It will be really complicated, right? But if we look at the form, we have x, y, z, right? We have also x, y, z. We have also x, y, z here, right? So we can take, because all is equal, the same lambda, right? So we can take the yz over 2x is equal xz over 8y, and xz over 8y is equal xy to z. Okay, at least this two is enough to find all possibility, right? So this will be that, and 8y squared, and then 2x squared. So we have this relation, and the other Now we have all these relations. Now we can look at our constraint. Our constraint is this. Okay, we can exchange x with 4y. So this will be 4y squared. And we have 16z squared, so we can multiply by 4. Right? So we can have this become 4y squared. And all this become this. And y squared is 4. So y is plus minus 2. So when y squared is 4, then x squared is 16. Right? So x is plus minus 4. And z, or we can say this is from 4z squared is 4. So z is plus minus 1. So we have 3 xyz now. But we are not finished yet. We need to take all this possibility to check. So we have x, y, z, right? So first, if all positive, right? And then maybe, and then this. So we need to take all the possibility that we can have. Then -4 to -1. And the -4, all negative, yeah. Okay, 8. Okay. And then check the functions, because the function is just x, y, z, right? So it's either having 8 minus 8, minus 8, minus 8, 8, 8, 8, minus 8. So with positive 8 will be the maximum, with the minimum, and the minimum will be the -8, right? So maximum is 8, and minimum will be -8. Okay. There's still some additional notes for the Lagrange, but I think I will save it for the next lecture. So next lecture will be finishing this Lagrange, and we can move on to the last chapter in our course. And you may notice, okay, so from the, at least by seeing this picture, from what we have learned, when we are talking about the chapter 14, we are talking about also chapter 12 and 13. So if I tell you that our final is only 14 and 15, it will include automatically chapter 12 and 13, because 12 and 13 are one of the main components to make the chapter 14. Okay, so I hope you get familiarized with the chapter 12 and 13 in how the factors behave and how you calculate each vectors. Okay, so I think that's it for today. We will see you again next week, and maybe in this weekend, maybe Friday I will announce something. But if not, then you can just try some exercise on chapter 14. Okay, but if I'm announced some maybe just a few exercise, some assignment, I will announce later on Google Classroom. Okay, so that's it for today. So I will stop the recording. And you can leave the Google Meet